So this is called, this is called a, I think I wrote that. This is a closed disk with center P, radius R. Closed disk. Similarly, if I take two intervals, and we'll make them those very special types of intervals that we talked about last time, closed and bounded intervals. So these are closed subsets of R. Well, I times j still means the same thing. It means the set of all points x, y, such that x is in I, y is in j. This is also closed. It looks something like this. Only now the points that are actually on the edges of the rectangle are elements of the set. So we can call this a closed rectangle. So you can see that it's closed, again, because the complement is open. In fact, it's a little easier to see that this is closed. It's easier to see that this is closed than to see that the closed disk is closed, because you can see exactly that this is the complement of an open set. And how do you see something is open? Well, it's okay if you see that it's a union of open sets. So in fact, can you see four easy to describe open sets that the complement of this set is a union of? So if this is A and this is B, if I take that region of the plane, union, make it smaller so it don't bring on the room. One, two, three, four. So if I have A, B here, this open set, so you can take the union of that with the union this, I have C, D. Now we can take this. So you take the union of those four open sets, you get everything that's not in the closed rectangle. So that's a proof that it's closed. And that's pretty much a full proof that it's closed. You just need to now see that these are open. So in fact, you could even do this. So in fact, so the complement of this set is the union of four what we call half planes. So remember we had the notion of a line in R2. So you could even take all points x, y, such that ax plus b dy is, well, you could choose greater than c or less than c. And depending on what you know about a, b, and c, a and b are not both 0. And so the set of points like this would be all of the set of points that are on one side of the line. This is called an open half plane. So the complement of the closed rectangle is the union of 4 open half planes. So recall that, so we certainly found with the subset of real numbers that when you have open sets, you have closed sets, but does every set have to be open or closed? No, that would be topology mistake 101. You certainly can have sets that are neither open nor closed. For example, if I take an open interval times a closed interval, it will look something like this. Could draw 2 line segments, like those 2 open line segments, and then so you can think of it graphically like this. This set is neither open nor closed. So perhaps you need a problem. Should give you something to think about. You can think of this as a simple problem. Again, it's one of these problems that it's not even much to write down. You just have to explain to yourself what does it even mean to say that this is neither open nor closed. Okay, so let's go back to the general notion of a topological space for a moment, and I'm basically going to give you some terminology along with a proposition. So this is terminology that is all over the place in topology. It's the idea of what's called a neighborhood. So a neighborhood of P in X, a point in X, we can just say it's any subset of X such that there exists an open subset of X. So when I say open, then you have to say, oh, he's talking about a topological space. So there's a collection T of open subsets of X. Okay, using that terminology, open. Such that there exists an open subset, let's call it U of X, such that, well, first of all, so P is in U, and U is in fact a subset of neighborhood A. So now we can draw pictures in the plane and actually know that there's really something going on. This could be a picture for the plane R2. So the idea in R2 is I have a point P. So this might be a neighborhood of P. In fact, it could even be the set in the previous example that's neither open nor closed. So you could even draw it that way. if you can find an open set, so a disk, for example, wouldn't have to be exactly a disk. So P belongs to the open set, and the open set is a subset of N. Then we just call that a neighborhood. Just a quick way of saying all of this is that N is a neighborhood of P. It's really the terminology to save us some time. So thus, it does not have to be an open set. It does not say that N is an open set. So thus, an open neighborhood, well, it's a neighborhood that's open. So that's just a fancy way of saying it's an open set that contains P. It's called a neighborhood of P. An open neighborhood of P. That's an open neighborhood of P is any open set that contains P. Okay, now this one is truly a definition, not just terminology. Definition. So I have a subset A of X. I have a point P in X. P is called a limit point. Of A. So you can even say this simply just in words. You just have to remember what the definitions are. And now I'm going to use the notion of a neighborhood. P is called the limit point of A if every neighborhood of P contains a point of A not equal to P. We can draw it pretty simply here. So here is A. So if I take a point in here, it's a point of A. Is it also a limit point of A? Well, as long as you can find, for example, even an open neighborhood of this point that contains at least one point of A that's not equal to this point, then it's a limit point. So in this picture, this point that's actually inside of A is a limit point. But now the interesting thing is that this happens even here too. So this point here might not actually be a point in A, but it's still a limit point because every neighborhood of that point is going to contain a point of A different from the original point. Notice that the same thing happens here if I make this picture, which is supposed to indicate that actually the points on what I just drew belong to A as well. Notice that this point here is also a limit point of A. So the difference here is that this point here, I'm trying to make you think that it's actually not an element of A. But this point here is an element of A. In fact, by drawing these pictures, you should see the connection between this idea and whether or not a set is closed. This set, if I include these points here, I could be talking about a closed set. But if I don't include those points, I'm not talking about a closed set. So the connection, so this idea of limit point gives an easy way to understand what it means to be a closed set. Here's a proposition. It's another way of understanding closed sets. So efficient way to figure out if a set is closed or not. It doesn't say whether or not it's open, it just says whether it's closed. Okay? So A in X is closed. This could even be a definition of closed. Closed means that the set contains all of its limit points. Contains all limit points. Okay. So, so for simplicity, if I have an open disk, so this point here is not in. Let's even to make it concrete. Let's say that I'm talking about the open disk, dpr. So this point here that's on the circle is not an element of dpr, but it's a limit point. But it's a limit point. So dpr, this open disk, is, well, as we've already discussed, is not closed. That's a quick way to see why it's not closed. It's because here's a limit point of the disk that actually is not an element of the disk. If you do this with a closed disk, so here I have dpr union with the circle, radius r. Now, can you find any limit points that do not belong to the set? You can't. I mean, these points are limit points, but they're in the set just like they were over here. But now you've taken this point here that it is a limit point, but it's not in the set, and you've included the circle, so you've included all of the limit points of the set. So this is closed. This one contains all limit points, so it's closed. So here's a way to think about closed without even really, I mean, yes, open sets are involved, but you're not thinking about complements of open sets, you're just thinking about limit points. Actually, it's a very nice exercise to show that these two things are the same. In fact, there's an idea here. So what if I take my set, and now I include all of the limit points. So this set is usually denoted by A with a line over it. A union, the set of all limit points. A. So if you do that, will it now will it be closed? Well, there's something to check, but it will. Is a closed set called a closure. In fact, it's the smallest closed set that contains A. And it's smallest in the sense if you take the intersection of all closed sets that contain A. It's the intersection. All closed sets that contain A. And we know, for instance, that the intersection of any collection of closed sets is closed. So, for example, what's the closure of, so to test this concept, what's the closure of the open disk centered at P? radius r. It's the closed disk. So the closure of an open disk is the closed disk. Contains the points on the circle. Or if you want, what is the closure of the product of two intervals? Product of the closed intervals. It's the closed rectangle. Although there would be one instance in which this is false, and that would be if this is the empty set. So if A is greater than B, this is the empty set, whereas this might not be. So yeah, if, for example, if A is equal to B, this is the empty set, and this is a one-element set. So this is provided. A is actually less than B. C is actually less than D. Okay, so we were just talking about some subsets of R2 that you can describe using equations. Everybody loves to use equations to describe stuff. So for example, lines. And in the curves we've seen, in fact the curves that we've seen are the conic sections. Are they closed subsets of R2? Are they open subsets of R2? Are they neither? Are they both? So what do you think? Is a line open or closed? A circle? Ellipse? Parabola? Pergola? What do you think? I think it's closed. So again, so these are important examples of closed subsets of R2. So you can either see that the complement is open, or you can think about it in terms of limit points if you want. These sets contain all their limit points. So you could use, so from here, you could use the fact that, so what are some things we know about closed sets? Is the union of closed sets always closed? Well, it sounds nice, but we even saw, for example, in the real numbers that the union of closed sets does not have to be closed. But as long as you only think about finitely many sets, it's always true. Thus, any finite union of such things is closed. So you can, so it's like if you want to make an abstract picture just by drawing these curves, make some lines, make an ellipse, make a parabola here, maybe a little circle there. something that you can draw like that, it's got to be closed. If you can, I mean, of course it's finite because I drew finitely many things. So also, in fact, this will take us back to something we talked about earlier on. So what's a line segment? In fact, well, actually, we'll talk about line segments more later. So also line segments, well, closed line segments are closed, hence the name. So in fact, this takes us back to the very first object that we studied in this course, which were graphs. Okay, so for example, a graph that you can draw in the plane, so a planar graph, so it's a subset of R2. Is it closed? Is it open? It's always closed. Okay. In fact, just from this fact, you can see that any planar graph R2 is closed. So you can take any of those pictures that we drew a while back, draw your favorite planar graph. In fact, you can even use some curves as the edges if you want. You can use parts of ellipses or parabolas, or we just stick to straight lines. Take your favorite planar graph. This is closed. R2. That's right, I wanted to... So the finite union of line segments or lines, circles, ellipses, and all those things, the finite union of those is closed. This is kind of a fun problem. Can you find an infinite union of curves that's not closed? So for example, so I wanted to point this out a second ago. What's this here? So I have the, this is set, I should put it like this. So I have the set containing the point 0, 0, and I take the union over all open disks centered at the origin, 0, 0, as the radius ranges from numbers between 0 and 1. What do you get? So, I have, for example, I have the origin, and now I have to take all circles with this radius. The radius can be any number between 0 and 1. So here's when you would have the radius 1, but notice I'm not including 1. But I can use any other radius, so what am I going to get? I'm going to get all points in there. So it's the closed disk. It's D 0, radius 1. And it's not open. It's, oh, I'm sorry. It is open. Yeah. That's the point. It's open. So that's, for example, why, that's an example where you have a union of closed sets, but it's not open. But as long as you stick to finite unions, by the rules of topology, it has to be closed, or else it's not a topological space. this is probably a good point to stop. So I guess we continue Monday at 2:30. No, we do not have classes next week, right? Okay, so we're off next week. The following week we will resume Monday at 2:30, correct? Okay, so I'll see you then.